Talking about some colligative properties of solutions. We talked about vapor pressure lowering, freezing point depression, and boiling point elevation. Again, so far in sort of non-ionic solutes being involved. And the idea, again, with the non-ionic sort of solutes is when we do dissolve those particles that are solute, we do get a kind of one-to-one relationship. So for every one particle that's dissolved, you get basically one particle that ends up floating around in the solution. And again, that's really important as to why we're not really sort of correcting for multiple sort of, say, particles are floating around in the solution, as it's sort of a one-to-one relationship. The presence of these particles, as we talked about, affects things like vapor pressure, freezing point, and boiling point. They, again, really sort of get in the way of the natural process of the solvent by itself if those particles were not present to be able to freeze and boil. And obviously, the result of the boiling aspect of it is, again, you get less gas molecules above the liquid and a lower vapor pressure that's happening. We've seen that we can use our freezing point, boiling point sort of information to calculate things like the freezing point temperature and boiling point temperature. We could also use it to figure out things like molar masses. We could also figure out how many grams of the solute needs to be dissolved. So you can use that sort of freezing point, boiling point information for a lot of sort of calculations. Again, when you look for the constant, it is based, once again, on the solvent, not the solution. So that is what you want to look for when you go to that table. Another sort of aspect that we're going to talk about in terms of solutions is osmotic pressure. And osmotic pressure is really the result of if you have, for example, two solutions. We'll see a better picture a little later on, I think, of this. But if you have like two solutions, say it's separated by a semi-permeable membrane. See, that's the membrane right there. And let's just say on one side you have, say, salt water, and on the other side you just have basically kind of say pure water. There is going to be a natural process that's going to occur, which is known as osmosis. And osmosis, as we will see in just a second, is the process where solvent molecules will flow across a membrane from a lower concentration to a higher concentration. So in this particular example, what's going to happen based on osmosis is water that's pure water has nothing dissolved in it, which means by definition it is a lower concentration than salt water, which is water with salt dissolved in it. So it has a lot more solute particles in it, is more concentrated. So the water molecules, the pure water, will flow across the membrane in an effort really to dilute down the saltwater part of the membrane or the other side. And it will continue to flow until it hits what is known as the osmotic pressure. And that is a pressure that's equal to basically atmospheric pressure that's pushing back down on it. And that will stop basically the flow of solvent molecules, water molecules from the water side to the saltwater side in this particular case. So at some point, the flow of those sort of solvent molecules will stop and we will get, it will hit its osmotic pressure. The osmotic pressure is needed to keep the liquid level sort of even on both sides of a membrane. And there is a formula, and this is the osmotic pressure. But for really all intents purposes, this formula is our good friend, the ideal gas law. Is pretty much this formula right here. That is pressure is equal to nRT over V, which is pretty much what that is. So to calculate the osmotic pressure, it is really the ideal gas law that we saw earlier. Remember that if we solve for N over V, N is moles, right? V is liters. That is molarity, which is where the MRT part of it comes from. This part, that is basically moles over liters, which is the molarity times RT. So the good news on this is it's still the ideal gas law, which means you still need to make sure everybody's in the proper units. Once again, the osmotic pressure will usually be in atmospheres when you solve for it because the volume should be in liters. The N should be in moles. The temperature should be in Kelvin. and R is still the same gas constant that we use with the ideal gas law, which is, again, this version of it, not the one that has energy. So you could solve for the osmotic pressure of a solution, and you basically will just be using really the ideal gas law here. We could also use this information to solve for other things like we talked about in the gas chapter, things like the molar mass of a gas, the density of a gas, that type of stuff, if you know sort of the osmotic pressure. So you could use this very similar to how we kind of use the ideal gas law in the gas chapter. But again, that's basically what it is. It just uses a different symbol to represent the osmotic pressure, which is, again, just sort of that symbol right there. So why don't you try one here? What is the molar mass of a protein? If 5.87 milligrams per 10 milliliters gives an osmotic pressure of 2.45 for at 25 degrees. So see what you come up with here. Okay, let's take a look. So once again, we're looking for the molar mass, which is grams per mole. And in this particular case, we know we have 5.87 milligrams of the sample, which really is the top part. We obviously do need to do a conversion to grams to get it to the correct units. Now, obviously, it mentions osmotic pressure, which makes you really just think about the ideal gas law, or if you want to use the fancy symbol, you can, I suppose. And here we would solve for the osmotic pressure. Actually, we were given the osmotic pressure. So we have the osmotic pressure given to us. We do have the volume given to us, which is 10 milliliters. And we do have the temperature, and we always have R. So we are going to really use sort of our ideal gas law here, much like we did when we were talking about this in the gas chapter, to figure out the moles part of it. So we just have some conversions to do. So our 5.87 milligrams, 1,000 milligrams in a gram will give us our grams in this case. So 0.00587 grams. Now we're going to solve for N in this case, which will be PV over RT. We do have a number of sort of conversions we need to do here. So first off, our 10 milliliters converted to liters. Remember, we still need to make sure everybody's in the proper units for our ideal gas law, even though it's osmotic pressure, still the ideal gas law. Our torr there needs to be converted into atmospheres. So that's our 760 torr is an atmosphere. That's going to give us 2.45 divided by 760, 0.003223. And our 25 plus 273, 298 Kelvin. And lastly, we always have R, right, which is our gas constant at that point here. So now that we have everything that we need in the correct units, we'll pop them in. So we'll go 0.003223. Our volume 0.010 liters divided by our R. And our temperature here. Everything's going to cancel out except for moles, which is good. So that's going to get us there. Looks like approximately 1.3183 times 10 to the minus 6 moles. That is the bottom part. We obviously have converted that to the top part. So now our molar mass here is going to be 0.00587 grams divided by our moles. And that will yield us a molar mass here of about 4453 grams per mole as our molar mass in this particular case. Any questions on that calculation? So I would say this one is pretty much identical to when we were talking about molar masses and gas calculations, or calculating the molar mass of a gas. Any questions on that one there? All right, so why don't you try another one here and see what you come up with. The molar mass of a lysozyme. What is the molar mass of a lysozyme? If you have 0.075 grams per 100 milliliters, gives an osmotic pressure of 1.32 times 10 to the minus 3 atmospheres at 25. Okay, so similar sort of calculation on this one. We're looking also for our molar mass, which are grams per mole. In this case, we're actually given the grams right off the bat, so not much to convert there. The rest of it, again, since they give us our osmotic pressure, we do again have the pressure, we have the volume, the temperature in R. So we will once again use this to get to N. In this case, our volume, 100 milliliters, will convert out into 0.1 liters. We would again take our 25 and add a 273 to get it to Kelvin for our temperature. And obviously our osmotic pressure actually is already in atmospheres, so we don't have to do too much conversion there. So N will equal 1.32 times 10 to the minus 2 atmospheres times our volume of 0.1 liters divided by our R value, 0.08206 liters atmosphere Kelvin mole, and our temperature of 298 Kelvin. Popping all those numbers in there, 1.32 minus 2 times 0.1 divided by 0.08206 and divided by 298. Gonna give us some moles here of, looks like 5.398 times 10 to the minus 5 moles. Now our molar mass will be our grams per mole, so 0.075 grams divided by our moles. Gonna get us here. About, we'll call it 1,389 grams per mole in this case. Any question on those calculations? Obviously, as well, if you're given volume, temperature, and moles or grams, you could just solve for what the osmotic pressure obviously would be in that particular cases. Any questions on osmotic pressure here, calculation wise? All right. Then let's talk about another important aspect of sort of what we've been talking about with these colligative properties, which is the idea that, again, colligative properties are based on the number of particles that are in the solution. The more particles you have in that solution, sort of the greater disruptive forces they're going to be for things like boiling point, freezing points, etc. Now, up until this point, we've done examples where we've talked about them being non-ionic, things that are covalently bonded, sharing electrons, carbons, hydrogens, all those kind of things. And again, in that situation, when we have, as I mentioned before, our non-ionic type situation that we're going to dissolve, when we go to dissolve that guy, we basically do get a sort of 1-to-1 relationship in terms of what we put in is how many particles end up in the solution. This is very different than what occurs when we are using an ionic solute. So if you are using an ionic solute, you actually do need to take into account how many particles you get per unit of ionic compound that you put in there. And we do need to correct sort of our calculations using what is known as the von Hoff factor, which is abbreviated with an I, is what that's for. So what do I mean by that? Let's say we dissolve not a non-ionic compound, but we dissolve sodium chloride into some water. When sodium chloride goes into water, you're going to generate a sodium ion and a chloride ion. This is no longer a one-to-one situation. When you dissolve something like sugar, the entire sugar molecule stays together and you get one molecule dissolved per one molecule. Here, this is now a 1-to-2 relationship, and you actually get twice the amount of particles in that solution when it's dissolved. If you took something like calcium chloride and you threw it in there, when calcium chloride goes for a swim, you're going to get a calcium ion, and you're going to get 1 and 2 chloride ions that are basically going to be dissolved into that solution. That is now going to give you a 1-to-3 relationship, and you're going to get 3 times as much particles in that solution as you had, say, with, say, sugar, which will only give you 1. So you do have to take that into account. And that is what is known as the von Hoff factor. It's actually a measured value. And if you measure the value or sort of experimentally find the value, it will be different than what you would predict from the actual formula. But in most cases, you could just predict from the formula what the I value would be. And what I mean by that is sodium chloride breaks apart into 2 ions or particles. The I value would be 2 for it. Calcium chloride breaks apart into 3 particles, 1 calcium, 2 chlorides. The I value would be 3 for calcium chloride. If this was sugar, like we did before, or glycerol that we were doing before, the I value is 1, which is why in those formulas where I put a little circle like we would do something here if there was more than 1 particle, there's nothing there because it's 1 basically in that formula. So for the most part, it will affect a lot of those colligative properties. So when you look at our freezing point sort of equation, in an ionic situation, delta TF would equal I, which is your von Hoff factor, times KF and M. So basically the same formula, but you do need to take into account in an ionic situation those extra particles that are going to be there. Same thing with our boiling point, I times KB, right? You could also do it for your vapor pressure. And you can insert it in. It is a little bit different a lot of times, though, when you are doing perhaps it with vapor pressure. Sometimes this I gets kind of used in the mole fraction part of it only. So sometimes it's not necessarily just kind of multiplied by it. It's used in the mole fraction part because it could be a situation where you're dissolving an ionic compound in water, for example. And really, you just need to adjust for the ionic compound, not the water part of it. So there is some situations where you may kind of use the I more so in the mole fraction part of it rather than that. But you do have to take it into account. So how does this really sort of affect things? Well, let's just say, for example, we had a solution that had a molality of 1.2, right? And let's say we did this in a non-ionic guy where I would equal 1. Let's say we did it with sodium chloride where I would equal 2, and calcium chloride where I would equal 3 in this particular case. And let's just say that we were looking at the freezing point and we use water as our solvent for all this. So as we saw earlier, 1.86 degrees Celsius molality is the KF for water. And the normal freezing point obviously is 0 degrees Celsius as we did before. So if we did our non-ionic in this situation, the change in the freezing point temperature would be KF times M. Once again, because it's non-ionic, really I is equal to 1, so we don't really need to put it in there in that particular case. And if we put in our numbers here, we would do 1.86 times our M, which is 1.2. And that will get us here 1.86 times 1.2. A change in the freezing point temperature of 2.32 degrees Celsius. Now, if we did this for sodium chloride, I in this case would equal 2 because we're going to get 2 particles. KF would be 1.86. Let's actually put the formula in there first, I think. So IKFM. All right, so we would have 2 for I. We would have our 1.86 degrees Celsius times our molarity, our 1.2. And in this case here, we will end up with 4.464 degrees Celsius. And if we did it for calcium chloride, our I would be 3, 1.86 degrees Celsius, molarity 1.2. So here we can plainly see the effect in this very simple example of the amount of particles that are in that solution. Basically, the least amount of particles affects the freezing point. It will only go down about 2.2 degrees. Sodium chloride's a couple of extra particles in that solution will make the freezing point drop even further. And obviously calcium chloride, which has the most particles that would be floating around in that solution, we see the freezing point drops even further, about almost 6.5 degrees or so, less than 0 in this particular case. So this just clearly illustrates the idea that we've been talking about, that the colligative properties, the more particles you have in that solution, the greater the impact is going to be on the things like freezing point and boiling point. And as you can see here, if it is an ionic compound that you are dissolving as a solute, you do need to take into account how many particles it forms. You need to figure out the von Hoff factor. And once again, you can just figure out the von Hoff factor from the equation. So again, if it breaks apart into 4 ions, I would be 4. If it breaks apart into 3, like we did here, I would be 3. It is close enough to the experimental values that in a textbook problem or in most problems, you could just use the formula to figure out what I is. Any questions on that there? And here is a table that shows the difference. This is, again, what you would expect based on the formulas. And experimental, you can see that it is slightly different, but for most purposes and calculation-wise, you could use the formula value for I and you'd be fine in all your calculations. Here again, that's iron 3 chloride, which would break into 1 iron 3 and 3 chloride ions, for a grand total of I is equal to 4 in this case, because you basically have 4 per particle that goes for a swim. Any questions on that there? All right, so why don't you try this here? What is the measured von Hoff factor if you have a 0.05 molality calcium chloride solution and it has a freezing point of 0.27 degrees Celsius? And obviously, this is ionic, so our Kf value will be for water in this case, right? And normal freezing point is 0 degrees Celsius. So in this case, we're looking for what equation. We have an ionic solute here, so we do need the I to be involved with it, and Kf times M in this particular case. So in this case, they did give us the molality, which is 0.05. We do have that this solution will freeze at minus, the temperature of the solution there will freeze at minus 0.27 degrees Celsius. Remember, as we talked about earlier, that is not the change in the freezing point temperature. So again, the change in the freezing point temperature will be our temperature of our solvent minus the temperature of our solution. In this case, water will freeze at 0 degrees Celsius minus our solution. That's going to be minus 0.2 degrees Celsius. Once again, this is how our negative sign goes away, because now this value is the actual change that occurred, again, not the one with the negative. So we have everything that we need here at this point, except for I. So we will solve for I in this particular case, which would be our change in freezing point temperature divided by Kf times M, and popping that in there, 0.27 degrees Celsius. divided by 1.86 degrees Celsius and M, and our molality, which is 0.05. Degrees Celsius will cancel, molality in this case will cancel, and just give us a number, which is what I is. And in this particular case here, we're going to be looking at about 2.9 as the measured value of I for calcium chloride, which is fairly close to the expected or value that you would get from the formula of an I is equal to 3 if you did from the formula. So you can see here the measured value is a little bit different than the actual value that you get, but very close. Any questions on that calculation? So once again, the I does need to come into play anytime you're dealing with an ionic solute that is being dissolved in a solution. If it is a non-ionic solute, you do not have to worry about it again because technically I is 1. So that's why we really hadn't used it on the previous examples that we did. Let's take a look at another one, which is a little slightly different. So earlier I mentioned a second ago that you can also apply the von Hoff factor to vapor pressure. And it is a little different depending on the situation of how you might apply it. So for example here, if we have a solution that contains 0.102 moles of calcium nitrate and 0.927 moles of water, we want to calculate the vapor pressure of the solution at 55 degrees Celsius. So what we're looking for in this particular case is what the vapor pressure here of our water is going to be in the solution, as we were given the vapor pressure of water in this case. So we do want to use our P of water is equal to our X of water here, which is our mole fraction times the vapor pressure of water under normal conditions. And as I mentioned before, the I does need to come into play, but it actually will, in this particular case, come into play only in the mole fraction part of the calculation, as we're really looking for sort of water's sort of vapor pressure being affected. So in this particular case, when we do the mole fraction, we do have for water the moles of water divided by the total moles in this case. But in this particular situation, we are dissolving calcium nitrate into the solution. And when we dissolve calcium nitrate into the water, we will get a calcium ion and we will get 2 nitrate ions in this case, which means the I value for calcium nitrate should be 3 in this case. The only place really where we see calcium nitrate is down here in our mole fraction, which is the moles of the water over the moles of the water plus the moles of the calcium nitrate. So this is actually the place where we're going to apply the von Hoff factor, which is the I value here. And if we do that, we will end up with the moles of water, which is 0.927 moles, divided by 0.927 moles for our water, plus, remember, this is a 1-to-3 relationship. So basically 3 times the moles of our calcium nitrate. Again, because we basically get 3 particles, right, for every one of those guys that we dissolve in there. So that's where we have to sort of take into account the I in this particular situation. And it's just with the calcium nitrate because water is covalently bonded and we'll get a 1-to-1 relationship. So if we were looking at water in this case, basically I is 1. So that's why we're not going to take that into account. So 0.927 divided by 0.927 plus 3 times 0.102. That is going to give us a mole fraction of 0.7518. Now we have our correct mole fraction. We already took into account that, and we have our vapor pressure of water. So in this case, we would go 0.7518 times our normal vapor pressure, 118.1 torr. And we will times that by 118.1. And that's going to give us something like 88.8 torr as the vapor pressure of water in this case. Again, we're just taking into account, and we still need to technically do that for the calcium nitrate part of this solution because it is the ionic part of it. Any questions on that? And again, technically speaking, I for this guy is a 1 and I for this guy is a 1, which again is why those guys are not really affected because it's a 1-to-1 sort of relationship. Any questions on that? Here we also see that the vapor pressure lowered considerably with the presence of those calcium nitrate. 3 particles in that solution, it went from 118 down to 88, right? So a very significant amount of depression in terms of its vapor pressure, and that is because as those water molecules try to escape, all that junk in the way, right? All those ions floating around in there are in the way of it. It's going to allow only a little bit of a lot less amount of water to escape the liquid, and that would result in less vapor over the liquid and a lower vapor pressure. Any questions on that there? Okay, so a couple other aspects of this here. For example, we do see this in regular life and stuff like this, for example, in food, ice creams, like soft serve, right? They put sugar in it, right? So that it doesn't fully freeze rock hard, right? And that's how you have sort of soft serve. Soft serve sometimes will have more sugar than say regular ice cream, and the more sugar lowers the freezing point, so it gives it a little bit of a different sort of texture, not as hard frozen at normal sort of freezing point temperatures, right? Because it would have to get much lower than what you would have say in your freezer to get it to fully become like rock hard and stuff like that. So you get more of a soft serve sort of ice cream because of all the sugar particles that are in it, versus say regular ice cream, which has a little less sugar perhaps in some cases, and will get obviously a lot harder in terms of its texture because it has less particles of sugar sort of floating around in it. Other thing that sometimes people do, right, is when they make pasta, right, they throw salt in it, right, thinking it's going to make it perhaps boil faster, perhaps boil at a higher temperature, right? And really, are you really affecting the boiling point temperature a lot when you do that? Are you going to make it boil faster? Who knows? You will definitely probably affect the boiling point temperature, right? Because you are adding salt to your water, right? So now you've dissolved some salt in your pasta water, which is going to increase the boiling point temperature and cause it to, for example, boil at a higher temperature, which may cook your pasta a lot faster, right? Because it is boiling at a higher temperature. But is the amount of sugar, probably not sugar yet through water or pasta, but the amount of salt that you add, really enough to make a big difference. So let's just say, for example, we wanted to have our pasta water boil at a temperature of, say, just a measly, maybe 2 degrees more, right? Celsius, rather than say 100 degrees Celsius, where normally, obviously, water normally boils at 100 degrees Celsius. So how much stage, how much sodium chloride would be needed, or grams of it? I mean, grams of sodium chloride would be needed to raise the temperature of water to 102 degrees boiling. If you had, I don't know, 4.5 quarts of water, so that's roughly 4.25 kilograms of water. So why don't you calculate how many grams of sodium chloride you would need to make that water boil at 102 versus 100. And obviously our KB in this case would be for water 0.512 degrees Celsius per molarity. Sodium is 2299. Chlorine is 3545, right? I'll do it as well. We'll see. So Made up numbers here. We'll see how we did. Okay, so let's take a look and see. So in this case, we are obviously using our boiling point. We are using sodium chloride, which is ionic, which means we do need to incorporate the von Hoff factor into here, which is I, our Kb times our molality in this particular case. All right, so my example here, we are going to try to just raise it 2 degrees Celsius by adding some salt to our water here for our pasta. So since this is boiling, the temperature of the solution minus the temperature of the solvent, that will give us 102 degrees Celsius to 100 degrees Celsius, and that's going to give us a change in the boiling point of 2 degrees Celsius. This is sodium chloride, which obviously when it breaks apart in solution in water, you get 1 and 2. So the I here is going to be 2 for it because you get basically 2 particles for every 1 that you put in there. And our Kb, once again, going to be for water, which is our guy here. That's going to allow us to solve for the molality, which is our moles per kilogram of solvent. We do know our kilogram of solvent, which is the water. That will allow us to get to the moles of the sodium chloride and then to the grams of the sodium chloride by using the molality here. Any questions on that there? So popping our numbers in here, we have a 2 degrees Celsius equals 2 for our I. Our 0.512 degrees Celsius per molality equals for molality. We're going to take these guys and divide it to the other side. And that's going to give us basically 2 divided by 0.512. It's going to give us a molality of, looks like 1.953 moles per kilogram of solvent. Any questions on that so far? So once again here, we're going to use our molality that we just calculated to basically figure out how many moles of sodium chloride that would be needed. And if we do that, we'll take our 1.953 moles of sodium chloride per kilogram of water. We will times it by our mass of our water. Roughly, we'll go with 4.25 kilograms of water. Those guys cancel. And that will get us 4.25. It's going to get us something like 8.3008 moles of sodium chloride. I want to know how many grams of sodium chloride that is, so I'm just going to add these two together to get the molar mass. So 2299 plus 3545, going to be 5844 grams per mole. So taking the moles of sodium chloride, we would need to make that big of a change there in temperature and times it by 58.44 grams per mole. I'm going to toss into my pasta water, I don't know, roughly 485 grams of salt. Feels like a lot of salt. A pound is 453.6 grams, yes? So I'm pretty sure nobody's dumping in a pound of salt into their water here. So you would need a lot of sodium chloride or salt here, right, to make the temperature of your water boil at 102 versus 100. In reality, maybe you dump in there, we'll be generous, I don't know, 40 grams for that amount of water. And that will actually change the boiling point only about 0.16 of a degree of Celsius. So it does, even if you toss a little bit of salt in there, depending on how much you put in there, probably the most that you're going to affect the boiling point of that water is by 0.12 degrees Celsius, depending on how much you put in there. So probably more importantly, why we put the salt in there is probably for taste and some other factors, like it prevents the pasta a lot of times from sticking a little bit more. But will it raise the boiling point? Technically speaking, it will. Will it cook your pasta faster? I guess it will, because it's slightly elevated the boiling point. But it's not going to make the water necessarily boil at a super higher temperature unless you dump in there a ton of salt, which I would probably not recommend dumping that much salt in there. Any questions on that there? Any questions on the von Hoff factor? Again, using it for ionic compounds or how to do it. Really, it's just the incorporation of that I factor, which you could get from your formula. And again, if it's non-ionic, pretty much I is 1, so you could sort of ignore it. Any questions on that? All right. Let's talk about a few other properties of solutions here to finish up. We talked a second ago about a semi-permeable membrane. That is a membrane, like in cells and stuff, for example. It does have holes in them, and these holes basically allow certain size molecules to pass through, and other size molecules are too big to kind of get through the holes. Now, there are things that are known as colloids. Colloids are much larger than solute particles in the solution. They are large molecules like proteins and groups of molecules or ions. They are a homogeneous mixture, which means they look the same. They do not settle out. Now, colloids are small enough to pass through filters like a filter paper. So if you had a piece of like a filter paper in their funnel, they are small enough to pass through filters, but they are too large to pass through like a semi-permeable membrane. There's also suspensions. Suspensions are heterogeneous type mixtures, which again, heterogeneous means you see different phases. These are oftentimes large enough that you can see it with your naked eye. So for example, if you had sand and water, that would be a suspension of sand in the water. You could clearly see the sand obviously floating around in the water and stuff like that. Suspensions are too large to pass through filters, so they can't pass through like a piece of filter paper, nor can they pass through sort of membranes as well. And here's a sort of a zoomed in shot of a semi-permeable membrane. Again, you can see there's kind of like channels which things can sort of pass through if they're small enough, but if they're too big, they will not be able to make it through. There, obviously, you can see a lot of the solvent molecules like water are small enough to pass through, and some of the ions that are hydrated are small enough to pass through. But these kind of larger guys, even though I drew the arrow passing through, will be too large to kind of make it through. And here we see that a suspension will settle out to the bottom, like if you had sand and water, the sand will pretty much drop to the bottom of the beaker. Solutions and colloids will basically be floating around. Against solutions and colloids can be filtered through a filter paper. And this is like a semi-permeable membrane, like a dialysis bag. It'll allow those smaller sort of solution molecules to pass through. But again, those larger guys are going to be trapped. Now, we talked about osmosis and osmotic pressure. And again, osmosis is the process where water molecules or solvent molecules do move from a lower concentration to a higher concentration, really in an effort to sort of balance out the concentration on both sides, for example, of a membrane. The osmotic pressure, as we just saw, we could calculate using the ideal gas law, PV equals nRT. The osmotic pressure does depend on the number of particles that are dissolved in the solution. The greater the number of particles, the greater the osmotic pressure. Pure water has no osmotic pressure as it has nothing dissolved in it. So it pretty much has no osmotic pressure. Another sort of measurement of osmotic pressure is osmolarity, which much like it sounds, is calculated by I times the molarity, I being, again, the von Hoff factor. So again, if you think about something that is an I value of 1 versus an I value of 2 versus an I value of 3, and if they all had, say, the same concentration of 2 molar, you could see that if you calculated the osmolarity for each of them, this would be 1 times 2, which would give us 2 osmolarity. The osmolarity for the next one would be 2 times 2 molar, which would be 4 osmolarity. And lastly, osmolarity 3 times the 2 molar, going to give us 6 osmolarity. So again, the more particles that are in that solution is going to have a greater effect on the osmotic pressure, as you can see just in that simple example there. The osmolarity, which again is another kind of factor of osmotic pressure, it increases with more particles present in that solution. And again, you can think about it, if you think about the ideal gas law, you know, the PV equals nRT. P is equal to nRT over V. The more particles that you have in that solution, which is the solute, this number gets larger, which means the top part gets larger, right? Divided by a smaller number, the pressure gets larger, right? The osmotic pressure gets larger because you have a greater number up there in top in terms of your calculation. Any questions on that there? And that's again what we see here. We have water in a brine solution, which is really like a salty solution. Water is going to flow through here until it hits the osmotic pressure. And that is what's going to stop that flow of continuous water molecules above it. Now, as you may know, you maybe heard of reverse osmosis. Reverse osmosis is when you apply a pressure greater than the atmospheric pressure. And what that does is it sends all the water molecules back the other way. And you have a lot of filters right about there to catch everything else. And that will push all the water molecules back the other way and sort of purify it a little bit by applying a pressure greater than the atmospheric pressure and cause basically the water to flow in the opposite direction. And you could kind of purify the water in that sort of sense. Now, when we talk about solutions, there's three types of solutions that you could classify, or three ways to classify a solution. One way is what is known as an isotonic solution. An isotonic solution is a solution that has the same osmotic pressure as body fluids. So what does that mean? If you take, for example, the classic example of this, which is a red blood cell, right? And if you put a red blood cell in an isotonic solution, you will have basically equal flow within and out of that basically red blood cell, as obviously there are basically like a membrane, right? Just going to allow things to flow in and out, and you'll have equal flow. Everything will be good. IV solutions are typically isotonic. When we talk about an isotonic solution, usually it's two types of solutions we oftentimes refer to, and that is 0.9% mass to volume sodium chloride, or a saline solution or some type of ionic solution, and a 5% glucose solution, sugar solution. So 0.9 and 5% are considered isotonic solutions. So if you have a solution that's greater than 5%, or less than 5% glucose, it is not an isotonic solution. And if you have a solution that's greater than 0.9% sodium chloride or less than 0.9% sodium chloride, it is not an isotonic solution. It doesn't necessarily always have to be sodium chloride, but that's a very common sort of one that's used. Again, it could be a ionic compound. So what happens if you have something less than that? That is what is referred to as a hypotonic solution. In a hypotonic solution, hypo means lower than. When you put a red blood cell into a hypotonic solution, the outside of the solution is actually less concentrated than inside the cell. So by the process of osmosis, all of the outside solution is going to run into the cell. That is going to cause the cell to swell and probably burst, which is known as hemolysis, which is probably not a good thing if it's your cells, I suppose. So this process of osmosis, hypotonic, lower concentration outside than inside, everybody's going to rush inside the cell in an effort to equalize the pressure on each side, and it's not going to be able to do so. It's going to cause the cell to swell. You could also have a hypertonic solution. Hyper means more than, and that is a solution that is greater than 0.9 or 5% glucose or 0.9% sodium chloride. And if you put a red blood cell into that type of solution, outside of the cell is now more concentrated than inside of the cell. So what's going to happen is the cell's going to decide, I want to go dilute down everything outside. And all of the fluid from inside of the cell is going to run out of the cell. And that's going to cause the cell to start to shrink and go through what is known as crenation, which is also not a great thing to happen in that particular case. So these are two effects that can happen if you have a solution that's either hypotonic or hypertonic. You can obviously not have a good situation for something like a cell or red blood cell, as water will either flow in or out of the cell through osmosis. again, in the effort to always kind of flow towards the more concentrated solution. So here's some pictures of that. Here, this is an isotonic solution, a nice happy donut, I suppose. Here is a hypertonic solution. Again, that's going to be like a donut hole. And a hypotonic solution, jelly donut going to pop open and start popping off at the outside there. So if we look at this, let's just say, for example, we put a red blood cell into the following solutions. We did 2% glucose. We put it into 1.1% sodium chloride. We put it into pure water. And we put it into 5% glucose. Are these isotonic solutions, hypotonic solutions, hypertonic solutions? And what's going to happen to the red blood cell in each of these cases? Will it shrink? Will it explode or swell? Or will it be okay? So take a moment and decide for each of those. All right, so let's take a look. So we'll start with isotonic. Again, 0.9% sodium chloride, 5% glucose, basically. So these are isotonic, and it is as simple as either it is that number or it's too high or too low. So if we start with 2% glucose, that is less than our 5%, which is isotonic. So that is going to make this a hypotonic solution. And the result of that means that outside of the cell is less concentrated than inside the cell. And that's going to cause, as we see in this picture, all of the solution to rush into the cell, and it's going to start to swell and basically burst. And that's not going to, again, go through hemolysis there. Not so great. If we look at the 1.1% sodium chloride, that is higher than 0.9%. That would make this a hypertonic solution. And that's going to give us our center job here. That means that outside of the cell is more concentrated than inside the cell. Through osmosis, the cell is going to release all of its fluid to outside in an effort to dilute it down. That's going to cause it to shrink. Also, again, not so great there, crenation happening. We'll go with pure water. Pure water is hypotonic, a situation where water is not so good for you because it has no osmotic pressure. And that means that if you put a red blood cell into water, outside of it, the water is going to be actually less concentrated than inside. And that's going to, again, cause all the water to flow into the cell there and start to swell. So water, not such a good thing in all cases. 5% glucose is isotonic, which means the cell will be okay. Nothing will happen to it. We'll have equal flow in and out of the cell because the osmotic pressure is the same inside and outside, basically, of the membrane. Any questions on any of those there? Now, lastly, dialysis is a process similar to osmosis. It allows small solute molecules to pass through, and it does prevent larger molecules to pass through. Obviously, in our body, we have dialysis that occurs. We sort of filter out bad things from our body using our kidneys and so forth. In the laboratory, sometimes people will use dialysis. For example, if you're working, say, on a protein or something like that, that maybe that protein's in a specific sort of pH environment. You can put your protein in a dialysis bag, for example. You can put it into a solution that is buffered at that pH. You let it sit in there for a while, and it will equilibrate to basically the same environment, say, that it is in the body or something like that. So in the laboratory, sometimes people will use this type of situation to do that, to sort of get things into the right environment and equilibrate things in the right environment. This dialysis bag, although you may not be able to see it, also has kind of holes in it. And again, those holes are going to allow certain size particles to be able to pass through in and out, and obviously prevent larger particles from exiting the bag and so forth. As you can see, these sort of larger particles get kind of trapped in the bag. the smaller guys are able to sort of flow in and out with no problem.